Hello and welcome to this episode of Math with Martinez. We are in our series on exponential functions and equations, and we're continuing this discussion on graphing exponential functions. So, I have a question for you once again. Have you ever gone to take a sip of coffee only to realize that it's gone cold when it should be hot and delicious and wonderful? It's disgusting like that, right? Now, the reason that this happens, the culprit behind this travesty is called heat transfer. And it is a type of exponential decay that is an important topic of studies for engineers, scientists, and even crime scene investigators. And the number E is used in some functions that describe this phenomenon. Now, what exactly is E? Well, that's what we're going to be looking at in this video. In the same way that pi is a symbol for a numerical value, E is an irrational number. And it's commonly used in advanced mathematics courses and in scientific and business applications. And it is the value that this expression below approaches as we would allow x to increase and increase and increase to infinity. And so I want to actually look at this with you all. We're going to try and complete this table, which means it would be helpful if we had our graphing calculator to do so. So let me grab this graphing calculator, clear out our functions that we graphed last time, and think about graphing this function and looking at the x values when x is 1, 10, 100, 1,000, 10,000, and so on. So let's go ahead and put this expression in here and call it our function. So there we go. We've got 1 minus the ratio of 1 to x being raised to the x power. And we're going to go ahead and look at the table here. At 1, it is, oops, did I raise this to the wrong power? Oops, I forgot. I wrote it as minus, but it should be plus. My bad. This should be a plus right here. We're adding this amount. My bad. Okay, come in here, edit this. Okay, look at the table. Okay, so at 1, we should have 2. Now let's scroll down to 10. At 10, it's approximately 2.59374, and it does keep going, but that's just the approximation. If we were to scroll all the way down to 100, which I can actually do much quicker by just going right here to table set, and instead of doing independent, I'm going to select ask. And then when I go to my table, I can actually type in 100 and see what it is. That's super handy. It is 2.70481. And if I want to go again and find even more, let's go to not 100, but 1,000. There we go. At 1,000, it's 2.71692. So I am keeping and continuing to plug in larger and larger and larger and larger and larger values for this graph, looking at what's happening here as we go out to infinity. Now 10,000. What do we get? 2.71815. And ladies and gentlemen, if we kept going and plugging in even larger values, we would be approaching what is that value E. And E is approximately 2.71828. That is the decimal approximation of pi. Of course, this value goes on forever. It never repeats, it never terminates. And this, what you just saw right here, this, let me close this out. This expression we're going to see has a relationship with a very frequently seen application dealing with finance. And so we're gonna see just exactly why this is so very helpful here in the future. But for now, what we've done is just kind of seen, okay, E is this value. E is the value that this expression approximates. If we were to go out to infinity, allowing these x values to get larger and larger and larger and larger, the value that it's approximating is E. So the graph. What does the graph of an exponential function whose base is E look like? Well, it's going to look like our other exponential functions, but the heights at those points are going to change just ever so slightly. So again, let's grab our graphing calculator and see. When we take E, which is this button here, kind of between 7 and 4, it's in blue, so I need to press my blue key first, the second key, and then raise that to the x power. And then we'll graph it. You see it's got that typical exponential curve where it's very flat and then grows very quickly. Let's look at the table so that we can get a better idea of those values. Oh, I'm going to put my table back in auto. Sorry, I clicked the button too many times. There we go. Okay, so let's go back to the negative values. You can see they're very small, but then at 0, it is at a height of 1. At 1, it's at that decimal approximation of E, which is 2.71828. So I'm approximating, oops, that's too low. Right about there. And then at 2, it's at a little above 7. And then at 3, it goes off the charts. So this graph, very flat lined up until its y-intercept. Then it grows very quickly, just like that. And once again, our key features that we saw before, the domain, the range, the end behavior, the y-intercept, and the asymptote are exactly the same as what we saw for our functions before. So I have this wonderful, beautiful shortcut that I'm going to take here. And go ahead and say ditto. It is the same for this function as well. But what we see here is that the rate that it's changing, like we saw in these lessons before, the rate at which it's changing each time is according to its base, what we highlighted here in pink. And that base for the natural base exponential function, that base is E, that number that this expression is approaching when we allow our x values to increase to infinity. That's it for this video. And until next time, stay fired up.